Hi, this is Gary Stafford, a Principal Solutions Architect at Amazon Web Services. Today we're going to be exploring the topic of building a video search agent with TwelveLabs on Amazon Bedrock using Strands agents and OpenSearch. For our agenda, we have 3 parts. First, I'm going to do a brief code review. All of the code for this project is available in open source on GitHub. Next, I'm going to be demonstrating the agent through a terminal interface. So I'll be showing you the basics of Strands agents and some of the capabilities of our application using a terminal interface. Once that's complete, we'll jump over to a conversational chat application built in Gradio and interfacing with our Strands agent, our models in Amazon Bedrock, including TwelveLabs Marengo, TwelveLabs Pegasus, and Anthropic Claude Sonnet. Let's get started. So I've switched over to a mermaid diagram of our code just to give you a high-level understanding of how our code is structured. So starting at the very top, we have different UIs. Today we have a Gradio conversational chat UI, and we're going to interact with our Strands agents through the Gradio UI. I also have a basic terminal application, and we'll be interfacing with the same Strands agent through the terminal to get started just to see some of the basics. Both the Gradio UI-based application and the terminal-based application both have logging. The Gradio application actually outputs its log directly to the UI so we can see what's going on behind the scenes as we're asking questions of the agent. Same with the terminal-based application, we're just outputting the logs right back to the terminal. Both of these UIs access the Strands agents, which is in a separate class in a separate Python file. That's the search agents Python file. The search agent Python files instantiates our Strands agent. It calls Bedrock on the back end. It calls Anthropic Claude 3.7 Sonnet on the back end. And it has access to several custom tools. Now those custom tools give it the ability to do a couple different things. If you're familiar with TwelveLabs and Marengo and OpenSearch and semantic search in general, you know that in order to perform a semantic search, first we need to convert a text string, our query, into a dense vector embedding. And then we perform a semantic search against OpenSearch using that dense vector embedding. So we've given the agent the capability to create a dense vector embedding from a user input. We've also given it the capability to perform several different types of searches depending on the user's query. It can perform a semantic search, and in this case we have a set of TV commercials. You can think of those as short videos, and those TV commercials are in an index in OpenSearch. The agent has the ability through custom tools to perform a couple different types of searches. It can perform a semantic search and return a list of videos. It can also perform a semantic search and return a list of video segments. So segments within those commercials that show a certain thing that we're looking for. Maybe it's a car, maybe it's a celebrity, maybe it's a certain food product, or maybe there's an audio excerpt we're looking for. With TwelveLabs Marengo model, we've created dense vector embeddings of the commercials, and we've created 3 types of dense vector embeddings for each segment of the commercial. So we've created a visual image dense vector embedding, visually what's going on in the commercial. Also, if there is text displayed in the commercial, we should also be able to understand that and analyze that. And lastly, we have an audio dense vector embedding. So if there's audio in the commercial, and most of these commercials obviously have audio, we can also ask questions of the commercial, and we'll be able to query for those commercials which match our query for different types of audio input: image, text, and audio. We have dense vector embeddings for all of those. Those are included in the OpenSearch index. And we should be able to use the agent to ask questions and query our index of commercials and be able to return results based on those different types of queries. And lastly, in addition to semantic search for both videos and video segments, we also have a keyword search. So if you've seen any of my previous videos or read my blog post, you'll be familiar with the documents that we've created in Amazon OpenSearch. In addition to having the dense vector embeddings, we also have things like a title of the TV commercial. We also have a brief summary of the TV commercial. So in addition to the multiple dense vector embeddings which describe different parts of the commercial, we also have a text-based summary of the commercial. And lastly, we have keywords. We've used TwelveLabs Pegasus model to create a title, a summary, and a set of keywords. So that's our code. I'll just jump briefly over into Visual Studio. All of the code is available on GitHub, and you can see the corresponding files. So as we talk through the different files on the screen here in our mermaid diagram, those are all available through the GitHub project. And then in addition to all that, there is a README file. There's instructions on getting started. I'm not going to go through all of that today. I would recommend setting up a Python virtual environment. You install all the requirements, so there is a requirements.txt file. I've already done that, so I'm going to start this demo in my virtual environment. I've already sourced my virtual environment. And the other thing I've done is set my credentials on the command line. Again, the Strands agent is going to use Amazon Bedrock. So the agent is going to be using a model on Amazon Bedrock. That gives it its reasoning capability. That gives it its general knowledge. its ability to use tools. You don't have to use Amazon Bedrock. Strands allows you to use multiple model providers or model platforms. We are going to be using Amazon Bedrock today, and again, I'm going to be using Anthropic Claude as the model of choice for this demonstration. We're also using OpenSearch. Again, I'm not going to go into much detail. I would recommend you view my 2 previous videos in my blog post. I'm running OpenSearch locally with Docker. If I switch over to the dashboard for a moment, we can take a look. We can see here that I have OpenSearch running and OpenSearch dashboards. And I have the index already created, and I've indexed those approximately 50 TV commercials into this index. I have 2 containers, OpenSearch and OpenSearch dashboards. I've created an index already, and I've indexed 50 commercials. All of that was covered in my previous 2 videos. So really, this video is all about agents. In our previous videos, we created the OpenSearch index, and then we wrote code, and we accessed the APIs for OpenSearch through the OpenSearch library. We wrote the code to perform specific queries. With an agent, we're able to take those different types of queries, make those available as tools to the Strands agent, and let the Strands agent decide which tools it wants to use. Doesn't need to create a text embedding. Doesn't need to pass that text embedding to OpenSearch as a semantic search. Doesn't need to perform a keyword search. Does it not need to perform a search at all? Maybe it can answer the question without actually creating a text embedding and performing a semantic search or a keyword search. So we're going to let the agent decide. We've simply provided those tools similar to the code that we wrote in our Jupyter notebook previously in the previous videos. That same code has now been turned into tools, and we've simply given it to the agent with a description, and the agent will decide which tools it needs and when it needs those, depending on the type of questions that we ask. The most important part of the README is the search examples. So I've written some search examples. I'm going to be going through a couple of these today in order to demonstrate the capabilities of Strands agents, both from the terminal interface and then the Gradio interface. All of these examples that I'm going to be going through today are included in the README file. So let's go ahead and get started. The first thing we're going to do is start the terminal interface and just show you some of the basics of Strands agents and some of the capabilities of Strands agents. So I'm going to jump over to my terminal and we'll get the terminal up and running. I started the terminal.py file, and we're just going to interface directly with the agent through the terminal. I'm going to run the query, then I'll explain to you what's happening. What is the square root of the sum of the current year, month, and date? Now, if you've worked with large language models before, 2 of the basic capabilities which large language models struggle with are math and then the current date, because the cutoff date for the training of the model is the last date that it's aware of. So it would not normally be aware of the current date today, and most models would struggle with even basic math. So let's try out our example. So what is the square root of the sum of the current year and day? Now, in addition to the tools that I told you about, I've also given it some capabilities to access some of the basic tools that are built in as part of Strands agents. The nice thing about Strands agents, you're able to provide access to some basic tools that you don't have to write any code for. And in this case, I've given it access to 3 tools: current date and time. So there's a tool called current time. There's a calculator tool. And lastly, there's a shell tool, which gives it the ability to interact with the system and write shell commands. Current time, calculator, and shell. It has access to all those. That's what I'm going to use here for a demonstration. So I'm not going to do any searches on OpenSearch. I just want to show you some of the basics of how an agent works. These tools are made available through the search application. They're made available to the agent in addition to the custom tools that I wrote for OpenSearch and for Morango on Amazon Bedrock. And we can see here that we came back with the correct answer. It was able to determine that today is in fact August 16th, 2025. And it was able to sum those 3 numbers together, the year, the month, and the date, 2049, and then figure out the square root of that. Very simple example, but again, just asking a large language model that, most large language models would struggle because of its inability to do math. Now, it might have got some of that basic math, but most models would not have, and it would certainly have not known the current date and time. Let's just extend that example a little more just to show you how the shell tool works. So I'll drop that in. Divide your answer by the total amount of RAM in this machine in gigabytes. I want to take that answer, 45.27, I want to divide it by the amount of RAM I have. And we'll see something interesting. If you're following along in the logs, the agent is trying to solve that problem. It's trying to figure out how much RAM do I have in this machine. And you can see that it's failing. So it tried a couple different techniques. If we see tool number 3 shell, tool number 4 shell, tool number 5 shell, tool number 6 shell, it actually failed 4 times to find the RAM. It has the capability to find out how much RAM I have, but I haven't given it enough information yet. It doesn't know anything about my system. It doesn't know my operating system, for example. There's a few things that it might need in order to solve it. So it doesn't mean it can't solve it. It really means that I need to provide it a little more information. I happen to be on a MacBook today, Apple MacBook. So now that it knows that, it's probably going to be able to solve that. And you can see, in fact, that it did. I have 16 gigabytes of RAM, It was able to determine 16 gigabytes of RAM because I told it I was on a Mac. Now it knows what command it needs to run. We can see that it was able to do that the very first time. So tool number 7, shell, it was able to get the amount of RAM in the machine. It knew the math to use to convert bytes into gigabytes. And then it took that and divided by that original number that we determined earlier. So the square root of the sum of the current year, month, and day. And it was able to give me the right answer back. Again, we're just in a terminal, no fancy interface. We're not using any of the custom tools yet, but that's really the power of agents. And again, I'm using Strands agents. You might use other agentic frameworks, Crew AI, LangChain, or LangGraph. There's a number of popular agentic frameworks. I really like Strands agents, which is an open source framework that was developed by AWS, by Amazon. It's available on GitHub. You can install it. It's a Python package. That's what I'm using today. So that's the agentic framework I'm using. In and of itself, it doesn't have a lot of these capabilities. What makes this agent powerful is 2 things. Tools, in this case, some basic tools that are already part of Strands agents, which you can turn on or off. There's a number of tools you can allow the agent to have access to. And then the large language model on the back end. Now, today, I'm using Amazon Bedrock. Again, I'm using an Anthropic Claude model that I told you about earlier. You could use a number of different models on a number of different platforms. Strands agents doesn't limit you to Amazon Bedrock. The power of that model and the power of the tools allows the agent to solve these problems. And as we get more complex, we'll see how the agent's able to not only utilize these basic tools that I've given it access to, but the custom tools that I've written in order to be able to interact with the TwelveLabs Marengo and Pegasus models and with OpenSearch. One more simple example, and then we'll move over to the Gradio UI. So let's just see how the custom tools work. Now we're going to get into more details on the custom tools in the Gradio UI, but let's just do a quick one here. Find commercials featuring superheroes. Now I didn't tell it to use OpenSearch. I didn't tell it that it needs to create a dense vector embedding, which you can see that it's already doing here. We'll walk through this code in a moment. So it figured out that I'm looking for commercials. It knows that it has an index of commercials, but in order to access that index of commercials, and it has a number of ways that it can do that, it knows it needs a dense vector embedding if in fact it thinks that it needs to perform a semantic search versus other types of searches like keyword searches. In this case, it determined I do need to perform a semantic search, or that's the best way to solve the user query, the request that I've made. We can see here, if you look at tool number 10, create text embedding. So that's in fact the name of a custom tool. Let me convert the query into a dense vector embedding. So we can see here that using Amazon Bedrock, it converted commercials featuring superheroes. So it used what I input. It did in fact succeed. It created a dense vector embedding. Now, how did it do this? It used a tool. That tool has access to Amazon Bedrock, to the TwelveLabs Marengo model. So it called the Marengo model. It got a dense vector embedding back. Now that happens to be an asynchronous call. So in addition to that tool having access to Amazon Bedrock, because it's asynchronous, that embedding was written back to Amazon S3. It was able to retrieve that object from the bucket that it has access to, and then it was able to extract the dense vector embedding from that object, from that text file, from that JSON file. And then it was able to use that, and we can see here on tool number 11, semantic search for videos. I didn't ask for a keyword search. I didn't say necessarily I wanted segments of videos. I didn't use words that would suggest I wanted anything other than list of videos back. So it called the semantic search for videos, tool number 11. So that's the 11th tool call that it's made since I started this conversation. It passed in the dense vector embedding, and we can see here that we got some results back. The other thing that's interesting, I didn't tell it how many I wanted. I didn't tell it that had like the title, the duration, give me a description, tell me who's in that. Maybe there's some celebrities, give me a list of celebrities. I didn't give it any details. So it kind of decided, let me return this list. So we can see here, we queried that, and then we can see right here in the logs, based on my search, I found several commercials featuring superheroes or superhero-like elements. Here is a list of the most relevant. So we see here, Hulk versus Ant-Man, Coca-Cola, Super Bowl 50 commercial. Superheroes, no question. State Farm commercial with Arnold Schwarzenegger, not explicitly featuring a traditional superhero, but it stars Schwarzenegger, who is an action hero in many movies. The intelligence of the agent, or really the intelligence of the large language model that's powering this agent, and able to not only return those movies and explain why it returned those movies. And then we can see here LeBron James, and it says LeBron James is portrayed in this particular commercial in a larger than life manner. And then lastly, we have Reacher Breaks the Bullies. If you're familiar with Reacher, Reacher is definitely superhero-like in his strength. Really starts to show the power of agents. And I'm going to switch over to our Gradio UI, and that's going to be a little nicer to look at. Same type of output, we'll separate the logs, and it's also going to use a chat interface, and we'll see that. So user response or user and assistance in a typical chat or messaging type application. So let me start this application. The link to get this started is available in the code in the README file if you're not familiar with the particular address that Gradio starts on. So I started that up. Gradio starts on default, at least on port 7860, 127.0.0.1 or localhost. And again, a very simple UI. I really want to show the power of the agent. So I don't want to get distracted showing videos or showing previews of videos. It's going to be a lot of inputting text and getting text back and really looking at the agent and how we can use the tools and the intelligence of the large language model and this agentic framework to be able to ask complex questions of that OpenSearch index that normally you wouldn't be able to ask, or it would take a lot of code to be able to take these queries and break that apart and write methods or functions. We've given the agent a few very basic tools, and it's going to decide how to use these tools plus the intelligence large language model to answer these fairly complex questions that we're going to ask it. So this is the interface. I'm going to jump over and grab something out of the README here to get started. So let me grab this and then we'll take a look at it. I'll just paste this in here. Find commercials that feature soft drinks and provide a ranked list of the top 10 results based on score. For each commercial, include the title, a summary, the specific soft drink product or products featured. The score is a percentage, so it's going to convert the score from a float to a percentage, and the duration of the commercial, and there is a duration for the commercial in seconds. One thing to note before the results come back, this is a semantic search. If you're familiar with semantic search, it's not necessarily going to return 10 commercials that include soda pop, and you may think by the query, well, that's what I've asked it to do, but it's performing a semantic search. It's going to return the top 10 results, the K nearest neighbors, the 10 nearest neighbors to the dense vector embedding. It's going to convert my user input into a dense vector embedding. It's going to perform a semantic search, and since I've asked for 10, it's going to give me the 10 closest results. That doesn't mean that every one of those 10 results contain soft drinks. That means that those are the closest matches to my query. Because we're going to get some results back that aren't soft drinks, we can do some additional follow-up questions and queries to fine-tune that result. So let's see what this does. We can see here on the bottom in the logs, similar to the terminal interface, we're returning all of the logs in real time. And this is a really great feature. So we can actually kind of see what the agent is doing. We can see the large language model. We can see the thinking that's going on in the background. And here's what's really interesting. That large query that I asked that I just read through, the actual query that it used for the dense vector embedding is right here. Soft drinks, soda pop, cola, carbonated beverages, non-alcoholic refreshments. Based on my query, it then read and understood my query, passed that to the agent, to the large language model. It decided to rewrite or write a text query, which it passed to Marango. Marango returned a dense vector embedding, but it wrote the query itself, showing the real power of agents and of the large language model. So it created that dense vector embedding successfully. We see that in the tool call. And then if we scroll down here, the second tool that it's calling, again, this is a new conversation. The first tool it called was to create the dense vector embedding. The second tool it called was semantic search for videos. Passed in the dense vector embedding, and it got back the results. You can see those results here. You can see this is a chat interface. So here's my question, and then here is the response. And it does return it in Markdown. And it looks pretty good. Number 1 is a Pepsi commercial. Number 2 is a Coca-Cola commercial. Number 3 is a Poppy commercial, which is a newer soft drink product. And the fourth one is Coca-Cola. Now we get into like Tootsie Pops, IHOP restaurant, Big Men on the Cul-de-Sac, Day of Laughter and Play looks like a Doritos commercial. And you might be thinking, again, these probably don't contain soda pop. They don't, but again, this is a semantic search. So it's not only returning commercials that contain soda pop. I told it to return the 10 closest matches or the 10 nearest neighbors, KNN or approximate KNN, semantic search using dense vector embeddings, using OpenSearch. It's going to return the top 10 results, not necessarily the top 10 results that contain soda pop. So something to keep in mind. We can see at the bottom here that it did a little further analysis. That summary of soft drink commercials. I found at least 4 soft drink commercials that clearly contain soft drink. So it's missing, I think, one of the Coca-Cola. I think there was 5 total. Interesting. So not exactly perfect, right? We had 5 that were Coca-Cola UFOs, Coca-Cola with Hulk, and then Coca-Cola Global Gathering. So there was 3 Coca-Cola commercials. Interesting. Again, these models are not perfect. I'm also not using the latest and greatest or the largest Anthropic model. You may get results back. They may not be perfect. That's why there's a human in the loop and you want to check these. And that's why I'm showing these results. I'm not showing you a demonstration that works absolutely perfect. Again, this is an agent. It's using a large language model. Your choice of model, your choice of prompts, how you prompt it, your choice of the tools that you make accessible to it, the prompts that the agent has. So in addition to the prompt that I input, there's descriptions of the tools which I've input. There is a agent prompt which tells the agent what capabilities it has. All of those are variables that are going to impact the quality of the results and the accuracy of the results. Also the temperature. A large language model, and if you're familiar with temperature, it's often considered the amount of creativity it has, anywhere from usually 0 to 1. So depending on how you set that, you give it more or less creativity to come up with answers for you. No, I've set this relatively low. I didn't set it all the way to 0. But again, those are all variables that are going to impact the results of this. Gave me back what I wanted. It actually appeared as though maybe it missed one of the ones here. So let's refine that a little bit. Excluding results where the main products being advertised are not soft drinks. At the end of your response, list any omitted titles along with a brief explanation. And we'll see what it can do with that. So we see we got Pepsi, Coca-Cola, Poppy, Coca-Cola. I think the title of one of those commercials was Coca-Cola. It was actually a Doritos commercial. Tootsie Pops, IHOP, Big Man on the Cul-de-sac, Bud Light, definitely not Coca-Cola. So looks like that works. So I got 4 back that look like they are correct. And those are most likely the only 4, given the small number of commercials, 50 commercials. Those are probably the only ones that do contain a software product directly. A few more examples here just to wrap it up. Let me grab this and then we'll tell you what we're going to do. So this one, search for commercials featuring well-known celebrities from Hollywood, sports, or music. Return a list of the videos that meet that criteria. For each video, include the title, the name or names of the celebrities or celebrities shown, a description of their activity. So not only return the commercials in a specific format, give me a list of the celebrities and tell me what they're doing. Very complex. Could we solve this programmatically? Absolutely. But you can imagine if you're a developer, you're going to have to write a couple different methods. You might have to make a couple different queries of OpenSearch in order to get this information back. So not easy. Only return commercials where you can tell me who the celebrity is. You may know that it's a celebrity. It may be a person or an animated character, but if you don't know the name of it, let's exclude that. So again, a lot of detail here. Let's see what the agent and the large language model can do with it, given the tools that we made available. Okay, we can see that it returned some results. Let's take a look and see what it did. Again, our question, we're looking for commercials that contain celebrities. Those could be from Hollywood, from sports, or music. The criteria is you have to be able to tell us who those celebrities are, and we want to know what they're doing. So let's see what we got back. LeBron James. Okay, we got LeBron James. So title, which we asked for, the celebrity. In this case, there's one main celebrity. And the activities which he's engaged in. And they told us the product which we asked for. So that worked. Let's keep going, see if this worked. So we have a State Farm commercial with Arnold Schwarzenegger. Again, it was able to tell us who Arnold Schwarzenegger is. In this case, since we said, hey, that could be sports, TV, the movies, entertainment, different places where we might consider someone a celebrity, it's actually telling us that he's a Hollywood actor, maybe versus a famous sports figure, and the activities that he is part of. So let's just go down, we'll keep going. Yep, we have a Nike commercial, Serena Williams. Coca-Cola ad. Looks like we have celebrities from Marvel, Ant-Man, and Hulk. Now that's interesting. Let's keep that in mind. It was able to tell us who the celebrities are. We never said they had to be humans. We just said celebrities. Just looking down here a little bit more, Judge Judy is in a commercial, and it knows actually who Judge Judy is and gave us her real name also, so really interesting. Again, that's going to the general knowledge that the large language model has. Her name unlikely was in the description of the commercial. It might have been, I don't believe it is, but the large language model might also know who Judge Judy's real name is. So that could have come from OpenSearch, from maybe the summary of the commercial, or it could have came from the general knowledge of the large language model. Let's ask a follow-up question just again to look at the power of the model, and also conversational, right? So we're carrying on a conversation with the model. Very similar with a conversational AI chatbot, we would be carrying on a conversation with a large language model. The difference here is we're carrying it on with an agent who indirectly has access and is powered by this large language model, but also has all these tools available. And that's what really differentiates this type of chat application from a traditional AI chatbot application. So let me grab the prompt and we'll take a look at it. So eliminate any results that feature non-human celebrities such as cartoon characters. Again, we did have one with Ant-Man and Hulk. I think that was the only one. Let's run this and see what happens. Power of the agent to access tools when it needs it. Let's see what it does with this, and then we'll take a look and we'll see how did it actually solve this. So if we look down here, what you don't see is any more tool calls. It had these results in memory. It returned, I believe there was 8 of those. And then I asked a follow-up question. One way to do that was maybe I modify my query. I create a new dense vector embedding. I pass that dense vector embedding back into OpenSearch to the semantic search tool, and I get a new list back, which hopefully doesn't contain any cartoon characters. In this case, though, the agent, using its logic, I won't say it was smart enough to, because it could solve this a couple different ways, but the way it chose to solve it was look through the results that it had, use the general knowledge of the large language model to remove any commercials which contain cartoon characters. And we can see here that's what it did. So the following commercial was excluded from the list because it contained non-human celebrities. So it did exactly what I asked. Really interesting, and it shows the power of the large language model's ability to reason and the ability to use tools and to power that Strands agents in order to do that. Let's do one more and we'll finish the demonstration. And we'll do a 3-part question here. The first thing I'm going to do, I'm just going to say clear our current conversation. Keep in mind, sometimes you'll ask it a question and maybe you'll get the results you want back. This is conversational. It can store up to 20 questions in memory. You might ask it a question, and based on the previous questions you asked, it's using those questions and the answers as context, and that may not always be a good thing, right? So imagine you're talking to your friend and they suddenly switch the subject, but you didn't realize, and they ask you a question, and you answer that question within the context of the previous conversation. Same with an agent. We've cleared that, so cleared the conversation. How can I help you today? Search for commercials produced by automotive manufacturers. Provide a numbered list of 5 commercials, including the title of each commercial, its duration, and a concise 1-sentence summary describing its content. Now again, keep in mind, semantic search. That doesn't mean that it's going to give me 5 commercials back that were produced by automobile manufacturers. It'll create a dense vector embedding of that it's going to do a semantic search or a KNN nearest neighbor search. So it's going to get the 5 closest matches to that query. Those don't necessarily mean they're all going to be automotive manufacturers. So we can see here, as this is still working, tool call number 5, generate a text embedding using Amazon Bedrock for automobile, cars, vehicles, manufacturer, commercials, advertisements, automotive brands, Toyota, Honda, Ford, Chevy, BMW, Mercedes, Audi, Volkswagen. So it decided, based on my question, the best way to construct a query which it can pass into OpenSearch was to reconfigure what I asked it into this format. So this is the text string which created the text vector embedding. If we scroll down, we see that that succeeded, and then it called again semantic search for videos. It passed in the dense vector embedding and it got results back. Let's quickly take a look. Mitsubishi Outlander, Lincoln Aviator, Subaru Forester, again looks good. Another Subaru commercial with a puppy, that looks good. And then the 2025 Volkswagen Tiguan commercial. So it looks like it did a good job. Not a lot of preamble or postamble. It found 5. It knew that it had 5. It returned those to me. Let's follow up though. Provide a detailed summary of the 3rd commercial in the list. Include a description of its visual elements, any notable textual content or on-screen captions, and the audio features such as music, sound effects, voiceovers that contribute to the overall impact of the advertisement. And number 3 here is a Subaru Forester, a family adventure through nature. I asked it for a list of commercials. It gave me a list of commercials by automotive manufacturers, but now I want to know more about one of those. So again, the power of agents, the power of tools, the power of the large language model. So if we scroll down here, we can see that it's performing another dense vector embedding, detailed summary of the Subaru Forester commercial. And it's got some results back, so it was able to query OpenSearch, and it got back some information from OpenSearch, and then using the general knowledge of the large language model, it interpreted what I asked, then formatted the response in the way that it thought would answer my question based on the information that it got back from OpenSearch. I have not allowed the large language model to access the internet. So it didn't go out to the internet, look for this commercial, look for information on Subaru. It's built this strictly on the information that's contained in OpenSearch, the information that it got back, which included keywords, summary, title. And we can see here, so visual elements, textual content or on-screen captions, audio features, and then overall impact. Here's the one caveat. Is this accurate? You'd have to watch a commercial and read through this. Is this necessarily accurate? No. The large language model's temperature is not set to 0. The large language model is interpreting what was returned from OpenSearch. I'm going to assume that all of the statements that it's made here is accurate, like the visual content and on-screen captions, that there are these. You'd have to check. Create a way in order to validate the response from this large language model. I'm not going to do that, but I'm also not necessarily going to assume that this is absolutely correct until I validate some of these responses. One last question, just to kind of show you some of this conversational power working with agent. Identify the target audience for this commercial. You gave me a list of commercials. One of those was of interest. You gave me some additional information about it. Who's the target audience? Who's the demographic or consumer segment that this is designed to attract? And I've said include some details about relevant characteristics such as age group, interests, lifestyles, and purchasing behaviors. One way to probably make this better is to give it ability to access the internet, and then it may go out and actually look for the characteristics of that demographic. Maybe it can identify the particular gender or age category for this commercial, or maybe it's singles versus families, particular age group, particular gender, and then it could go to the internet and say, what are the characteristics? It doesn't have that ability. So I'm relying on the general general knowledge of that large language model. That may or may not be the best way to do this. What we can see here, let's just take a quick look at the results. So target audience analysis for 2025 Subaru Forester commercial. Based on detailed elements of the commercial, the advertisement appears to be primarily targeting the follow demographic and consumer segments. And we see here family-oriented adults 30 to 45 years old. If you've watched a commercial, that sounds pretty accurate. I would say that that's good. Parents with young to preteen children at a life stage where family safety is paramount. Again, it's a Subaru. That's why they bought it. Middle to upper middle income earners who can afford a mid-range SUV. Makes sense. Professionals who appreciate and understand the technical safety features of the Subaru. I'm not going to read through all of this, but again, looks pretty accurate. Might be ways to improve this if I gave it access to some more basic tools like maybe access to the internet or access to a knowledge base, which included demographic information or advertising information. It might have been able to refine this a little further. But again, it's only going by, in this case, the general knowledge of the large language model. So that's a quick demonstration of using Strands agents, which is an open source agentic framework developed by Amazon by AWS. I'm using OpenSearch on the back end. I have an index in OpenSearch of commercials. I built that using TwelveLabs, Marengo, and Pegasus models. Those are both available on Amazon Bedrock. And then the Strands agent is also calling Amazon Bedrock, Anthropic Claude Sonnet on the back end and using that general knowledge of the model in addition to the tools that it has, the basic tools through Strands agents, in addition to the custom tools that we created and gave it access to, creating a dense vector embedding with Marengo, accessing S3, performing different searches on OpenSearch. Given all that, we're able to interact with that agent in a conversational manner, be able to ask questions, ask follow-up questions, refine the responses, and get the answers back that we wanted. Very basic demonstration is really just starting to touch upon the capabilities of the agent, but really shows you the powers of an agentic system, of an agentic workflow, especially of an agentic powered conversational interface that sits on top of knowledge base. In this case, it's just a single knowledge base, OpenSearch, but you can imagine if we gave it access to additional knowledge bases, it's able to combine learnings from those, do even more complex analysis. I mentioned in the beginning of the video that there's 3 different searches that the agent can do: a semantic search for videos, a semantic search for video segments, and a keyword search. All of my examples so far have been semantic searches of videos. So let's do a semantic search of segments. So video segments, segments within the video. TwelveLabs Marengo breaks the videos up, the commercials in this case, into segments from 2 to 10 seconds and creates embeddings from them. 3 different types of embeddings. We have a visual image, a visual text, and an audio embedding for each one. All of those embeddings are part of the OpenSearch document. So we should be able to search the OpenSearch index for segments within commercials, within videos, and be able to return those just like a unique list of videos. So let's try that out. I'm going to jump back over to my README file. And I have a search here. Let me drop that in and I'll tell you what it is. Search for segments within commercials that show exotic vacation locations, such as tropical beaches. Provide a bulleted list of the top 5 results, ranked by score. For each segment, include a title, location if known, description of the segment, score converted to a percentage, and the start and the end time of the segment. Let's give that a try and see what we get. So following along, we can see that it started off by using the create text embedding tool. So that's a good start. And we see here the text embedding, the query which it used to create the text embedding from: exotic vacation locations, tropical beaches, paradise, resorts, island getaway. It then took that dense vector embedding that created using that tool, and it passed that to a new tool that we haven't seen before. It passed it to the semantic search for video segments, and that's the correct one. And we can see here that we got results back. So let's take a look at the results and see if it followed my directions. So we got a bulleted list back. We see bookings.com, location, beach scene with beach house and palm trees. And we got a description back of the segment. And you can see that we got the start and the end time. So this first segment happened to start at 0 seconds and go to about 5 seconds. Scrolling down, we'll just check some more. We have an Expedia vacation, Bali, Indonesia. That worked. Aerial view of a man riding a motorcycle along a scenic black sand beach. So the description looks good. And notice here the start time is 4.9 seconds to 10.1 seconds. The formatting isn't perfect. I could probably come back and ask it to fix the formatting so that it's in seconds. Maybe we'll follow up and do that. But overall, it looks like it worked. And you can see that it didn't return entire commercials. It actually returned segments within commercials to answer my question. Let's see if we can fix those start and end times so that they're in seconds and they're formatted correctly. So great answer, convert the start and end times into seconds. I'm just looking through, it looks like, and this is what I would hopefully expect, it didn't make the calls over again. So it didn't call Bedrock, it didn't call TwelveLabs Marengo model, it didn't go back and requery OpenSearch, it just formatted the output again so that it followed my directions, and it looked like that worked. So 0.0 seconds to 5.2 seconds, 4.9 seconds to 10.1 seconds. So that worked. It was able to adjust the output without going back and making additional calls, with additional cost obviously to call Amazon Bedrock and potentially OpenSearch if you're running OpenSearch in the cloud. So it looks like that works. So this is an example of video segments versus videos. Maybe one more search will just demonstrate keywords and we'll wrap this up. So I've restarted my application, I've refreshed the conversation memory, and I want to demonstrate the third search capability, the tools which we provided the agent. So again, we have semantic search by video, semantic search by video segment, and the third one was keyword search. So I want to finish this up by doing a keyword search. So let me switch back over to my README file. I have a search prepared. We'll input that and we'll talk about it. Find all videos that include the keywords family or adventure. Return a bulleted list of each video displaying the title, duration, and the relevant keywords associated with the videos. So if we're looking down here at the logs, we can see the tool call number 1, so we've reset our conversation, and we can see here a new tool, keyword search for videos. So that is the third search mechanism. We had semantic search for videos, semantic search for video segments, and we have keyword search for videos. And we can see that it performed a keyword search with a list of keywords, both family and adventure. And we can see that we got a few results here back. So let's take a look up here in our chat window. So we see our input here, our question. And we can see here that we did get the results. So Viking family, adventurous journey in a Hyundai Santa Fe, duration 75.1 seconds. So we did ask for the duration. And then if we look here, we do see family and we do see adventure. So that worked. Here's Ant-Man and Hulk, miniature Coca-Cola adventure. And let's take a look and see if we find out. We found adventure. Now I did ask for family or adventure, not family and adventure. So this also qualifies. It has the word adventure. And we'll just take a look at one more of these. Here we have a Temu commercial, 30 seconds in length, gave us a duration. And we see that we have family. So in fact, that has family, so that also worked. Looks like quite a few of the commercials within our index contained either the keyword family or the keyword adventure, and we got the list back just like we asked for it. Thank you very much. Appreciate your time today.